Okay, so let's do our sum of squares for these two groups of numbers. First thing I'm going to do, in order to do this formula, is to calculate the mean. So let's just do that quickly. I know you've probably already done it. Plus 10 plus 11 plus 7 plus 8 equals, we're going to divide by 6. So the mean here is 8.50. Okay, so that's the first step. Then we're going to sort of unpack this formula. So what we're going to do here is take each number and subtract the mean from it. So here we go. 6 minus 8.5. We're going to square that. Okay, and then 9 minus 8.5. And we're going to square that. And 10 minus 8.5. And we're going to square that. And so on and so forth. Okay, we'll do this 6 times. So this 6 minus 8.5 is equal to 2.5. We're going to square that. So this is 6.25. Okay. 9 minus 8.5 is 0.5. We're going to square that. So that's 0.25. Okay. And so on and so forth for each of these numbers. Then we're going to add these together. Okay, we're going to add these together. So the sum of squares then is 17.50. Okay. So make sure that you go through and that you do that and see that you get that answer. If you don't, let me know. Or go through it again and see if you can't figure out. We're going to get the mean. Then we'll do this for each number, square it. Then we'll add those together. Okay? So now if we move over to this distribution, let's get the average for that distribution. 572 plus 568 plus 569 573 Oh, I'm screwed up there. Okay, let's do this again. 572 plus 568 plus 569 plus 571 plus 570 plus 573 equals, then we'll divide by 6. 570.5, okay. 570.5 is the mean. And then basically we're going to do the same thing now. So this is 572 minus 570.5. We'll square that. And then 568 minus 570.5. And we'll square that. And so on and so forth. Okay? Now, when we do that, what we end up seeing is the sum of squares for this group is 17.5. Okay? And in fact, I do this purposefully for a number of reasons. So the examples I use, I try to use so that they demonstrate one of the concepts. And in this case, remember, we need to keep in mind, sum of squares is a measure of spread outness. Okay, sum of squares is a measure of spread outness, or a measure of variability is what we're going to start to refer to it as. And it's just mildly camouflaged here, but basically this is 6 numbers in a row. 6, 7, 8, 9, 10, 11. Okay, so 6 numbers in succession. That's the variability of these numbers. But likewise, this set of numbers is 6 numbers in a row too. 568, 569, 570, 71, 72, 73. And so the two groups are equally variable. The two groups are equally spread out, okay? And I do this purposefully. And one of the reasons that I use these specific sets of numbers is to try to show you in a real way that variability, spread outness, okay, is really independent of the size of the numbers in the data set. So here we are up in the 570s, right? Up around 570. In fact, the average is 570.5. Okay. Here, the average is 8.5. So these two distributions are located at different points along the number line, but they are equally variable. Okay, so the mean tells you where along the number line the distribution is centered, hopefully. If it's a normal curve, the mean is a good measure, right? The mean tells you the relative magnitude, the size of the numbers, where they're located on the number line. The sum of squares tells you how variable or how spread out the numbers are. If you have two groups with the same sum of squares, that means they have the same variability, even if they're located at very dramatically different locations on the number line. Okay? So let's see if we have this concept, because it's an extremely important concept here, and that is, what if we changed this number from 11? What happens if we change that number to 14? What do you think would happen to the sum of squares? Well, remember, please try to keep this in mind, because you're going to get caught up in the computations, right? Remember, sum of squares is a measure of spread outness. So if I take one of these numbers and make it more spread out relative to what it was, then this value will go up. And we could calculate that if you want to prove it to yourself. Like, the computations will prove the concept, okay? That's how it works. So if we had changed that number from 11 to 14, we would see an increase here. If we change this 6 to, let's say, a 3, we would likewise see an increase in the sum of squares. Let me ask this a different way. Suppose that instead of 11, we move this number, we change it to 8. Well, in this case then, the variability, the spread outness of the numbers would decrease, and so we would see a corresponding decrease in the sum of squares. Okay, that's how it works. Okay, let's do two more. Sum of squares here. Okay. So we're going to do. Let's do distribution F and G, and let me give you these numbers. Let's see. Let's just do 5 numbers here for now. Well, we'll throw in another one. Let's see. Let's do this. Okay. So let me ask you this question. Let's see if we can make a guess here about which of the distributions will have the larger sum of squares value. Which of these two distributions will have the larger sum of squares value? If you said F, you are correct, okay? And we would have a larger sum of squares value here because this distribution is more variable. It's more spread out than this distribution. Even though these numbers are larger, these are more spread out, okay? And so let's calculate it. Okay, let's calculate. So here we have our mean for F. And can we do this quickly? 12 plus 37 plus 58 plus 81 plus 20 plus 70 equals 278. 1, 2, 3, 4, 5, 6. Okay, 278 divided by 6. So our mean in this case is 46.33. Okay. And I'm going to double check just because I don't want to make a mistake. 12 plus 37. You should always double check. Why wouldn't you? Okay. 278 divided by 6. So our mean 46.33. Okay. And then what we're going to do is we're going to use our sum of squares formula. So we're going to do this. 12 minus 46.33. Square that value. 37 minus 46.33. And we'll square that value. 58 minus 46.33. And we'll square that value. And so on and so forth. And then we're going to get our sum of squares. And let's calculate this. Okay, 12 minus 46.33 equals. Oh my goodness. So 1178. Everybody with me? 0.55. Okay. 37 minus 46.33 equals. Square that. 87.05. Okay. 58 minus 46.33 equals. We'll square that. 36.19. 81 minus 46.33 equals. We'll square that. 1202.01. 20 minus 46.33 equals. We'll square that. 693.27. And then finally, 70 minus 46.33 equals. We'll square that. 560.27. Okay? I think that is correct. I'll rely on you to check me on that and let me know if I'm incorrect. Okay? Let's add these together now. That's what this does. So what we've done here is we've subtracted 12 minus 46.3 and then squared that. That's what that is. Okay. Now we're going to add these together. So 1178.55 plus 87.05 plus 136.19. And the answer for sum of squares for this group, for group F, is 3,857 0.34. Okay. We will talk about this more as we move forward. One of the things that happens when we do these computations, is people might get this number. And I've seen this repeatedly in my classes, and then people will think this is the wrong answer because it's so large. Well, we're going to deal with how large sum of squares is. It's not going to be nearly as large for this group, and I would ask you guys to do this for practice, of course. Okay. So see if you can get that sum of squares as well. So this looks like a large number, and we'll get to it. But let's think about, when you see that and you say, oh, I must have made a mistake. That seems too large for some reason. Let's think about what's happening here conceptually, right? Instead of just going through the computations, let's think about what's happening. We're getting a deviation score. That is a deviation value for each of the scores. This was 34 points away from the mean. Okay, just this. And then, of course, we squared it, which is going to make it even that much bigger, right? And so here we have, this is the contribution just from this number, okay? This is the contribution just from this number, and so on and so on, okay? When we add these up, the sum of squares gets quite large. And in fact, if we had sort of a real data set with, let's say, 50 or 75 or 127 numbers of this ilk, we would have a sum of squares in the tens of thousands, maybe hundreds of thousands. And I certainly in my career have seen sum of squares in the hundreds of thousands, okay? If the numbers are quite variable, then we're going to see a large sum of squares. We'll talk about what we're going to do with this. We're not going to leave it like this, okay? But it gets pretty large. Let's do the other one just for practice. If you would like, you can pause the video now. In fact, I would suggest to pause the video, try to do this, come back and see if it matches what we're doing. Okay, let's see. 121 plus 125 plus 127 plus 131 plus 120 plus 125. Okay, divide by 6, and the mean is 124.83. Okay. When I get a mean like that, I'm always, once I get my answer, I look at the numbers. Does that make sense? And it seems to make sense here. I look over here. It's harder to see if it makes sense, but I mean, at least that's in the ballpark. If I got an answer of 107, I would know that I was wrong, right? This is a common theme for this class. Oftentimes you know when you're wrong, you just don't know if you're right, and people erroneously thinks that that's not helpful, but it actually is, because if I'd come up with a 107 here, I would know that that's not the average for these scores, and so it gives me a cue. I can go back and redo it. So at least this is in the ballpark. Again, let's quickly go through our sum of squares. So 121 minus 124.83 equals, we're going to square that, okay? So that was 14.67, okay? 125 minus 124.83, small number in that case. We'll square that. Wow, 0.03, okay? 127 minus 124.83, square that, 4.71, 131 minus 124.83 equals 38.07. 120 minus 124.83 equals 23.33. Okay. And 125 minus 124.83, another small one, 0.03. 1, 2, 3, 4, 5, 6. Let's add these together. And I believe that the answer for sum of squares here is 80.84. So, by the way, I certainly do not want us to lose track of the concept. The concept is the most important point. You also have to do the computations, okay? But the concept is the most important. The initial question I asked you was whether you thought group F or group G would have a larger sum of squares. And I think that my presumption is that if you keep track of the concept, sum of squares is a measure of spread outness, sum of squares is a measure of variability, that you would look at these numbers and say, wow, these are more variable, they're dispersed wider, right? There's more variability here than there is here. These numbers look like they're closer together. And so your guess was that group F would have the larger sum of squares. And you were correct. Okay? Now, it's time to take a moment in this course to give yourselves a pat on the back. I mean, I really think it's important to do that. And that is, this is a completely new concept for you in terms of sum of squares, variability, spread outness. And you were able to look at these two groups of numbers and tell me this one should have a higher sum of squares. I can tell you right now, I have met graduate students, I've met faculty who look at these and say, which is more variable? It's like, I don't know. Or more specifically, which was going to have the larger sum of squares. And a lot of people just don't know that. They're going to put it into a computer program, it'll tell them, but they're losing the concept, right? So I want you to embrace that concept. It will serve you well, okay? If the numbers are more variable, and this is a measure of variability, then this is going to be larger here. If the numbers are less variable, then we're going to have a lower value for sum of squares, okay? And, you know, the sort of the opposite of variability is consistency, right? These numbers are more consistent than these numbers, okay? These numbers are less spread out than these numbers, okay? So that's it. I'm going to leave this information up here, and what we're going to do is make a quick switch here, and we're going to use a different formula for sum of squares. When exam time comes, I'm not going to allow you to use this formula. Now, I know some of you are already thinking, well, if we're not going to use this formula, why the hell did we learn it? Because this is the concept, okay? And in fact, this is called the conceptual formula. I'm going to switch over to the computational formula. It is, some people say it's easier. It's a better way to calculate sum of squares, but the meaning is a bit obscured in the new formula, okay? But it's easier to plug in numbers, and in fact, even though there's some rounding, there's less rounding when you do the computational. So here's the new formula, and this is the formula that I want you to use. I want you to be comfortable with this, and like with any math, comfort comes from practice, 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 okay? Here's what we're going to do. Okay, can we see that? So we need to understand there's two components to this formula. This component tells you square each of the numbers, square each of these, and add those up. This tells you add up the numbers first, because we're going to work from inside our parentheses outward. Add up the numbers first, then square. Of course, then divide by n. Okay, let's do it this way. And what I want you to do is, I want you to do this formula for group G. We're going to do it for group F right now, but I want you to do it for group G. We should come up with the same numbers. If there's a slight difference, this one is actually more accurate, but usually it's spot on, because this formula is derived from this formula, okay? Now again, I don't want people to be resistant to this. You have to trust me on this one, okay? This is the definitional or the conceptual formula, because you as a student should be able to see this. This tells us how far apart each score is from the mean. How far away is this score from the mean, right? That's what this tells us. That is the essence of variability. How far is this score away from the mean? The square was just to get rid of the negative. We have to do that. But that's what it does. It just gets rid of the negative so we don't have this zero balance, okay? And then this says, do it for all of the scores, not just one. So by looking at this formula, you should be able to see the definition, the conceptual basis of sum of squares. When we look at this one, it's not so easy to see, okay? But I can get the sum of squares without having to get the mean first. Plus, I'm rounding here, and whenever you round, you're really infusing error into your value, okay? Let's see how this works for group F, okay? What we're going to do for this first portion is we're going to square each of the numbers and then add them together. So 12 squared is 144. 400 squared, 20 squared is 400, I know that. 37 squared is 1369. 58 squared, 3364. 81 squared, 6561. 70 squared, 4900. This first, we're going to square each number. We're going to add those together. Wow, okay, 144 plus 1369 plus 3364 plus 6561 plus 400 plus 4900. 16738 minus, now we're going to add all these numbers together. That's what this is. Do the inside parentheses first. 12 plus 37 plus 58 plus 81 plus 20 plus 70 equals 278 squared divided by 6. So here's how I would do it. Part of this is managing your numbers, right? 278 squared divided by 6. So this is 12,880.67. Okay. And so we're going to subtract that. $12,880.67, and that gives us 3,857.33. Okay. Notice same. This is rounding error. This actually, I trust this one because it includes less rounding than this. But it's the same formula. It's just written in a little bit different way. Again, please trust me on this one. This may seem harder than this, but as you get practice, it's easier because you can just cue off of these raw numbers and get your sum of squares, okay? So this is the formula that I want you to use for computations. And now there's video evidence. If you use this formula on the exam, I will not give you full credit, okay? That's the way it is. I want you to learn this. I want you to understand what this means. You can see the essence of variability here. How much does the score vary from the mean? We're going to do that for all the scores. This gets rid of the negative. This one, it's not as easy to see that, okay? All right, so please practice with group G. See if you got the same answer as when we did it this way. I hope that you will. There's practice problems at the end of each chapter. Go through the book and do the sum of squares. We need to get comfortable with this. Okay, we need to get comfortable with this. There is still a problem here because, like I said, this looks like a huge number. I know why it's so large, but it doesn't seem like this number is related to this group of numbers, right? It doesn't seem like that should be related to this. We know why it is, right? We're squaring all the deviations, but it's a little bit weird. All we know right now is a group with a higher sum of squares is considered more variable, more spread out. Or I can say it sort of in a complementary way. I can say a group of scores that are more spread out are going to have a higher sum of squares. So I'm at the point where I can compare two groups, but I'm still left sort of wondering what the hell this means, right? 3,857.34. And so in the next video, we're going to talk about that a little bit more, and we're going to do some mathematical massaging so that we get to a number, a measure of variability, because that was our initial goal, that sort of makes sense to us, okay? So that'll happen in the next video.